call. So last class I introduced basic electronics course, objectives, course objectives, and the application, some of the applications of basic electronics. That is electronics. So what is the basic difference between the electronics engineering and electrical engineering? Last class I gave some introduction to electronics. So what are the basic differences between electronics and electrical engineering? Anyone please? So electronics is concerned with flow of current in the semiconductors, whereas electrical engineering is concerned with flow of current in the conductors. So last class we have defined current, voltage, and charge. So can anyone recall? So what is current? Please respond. Am I audible?
Flow of charge per unit time. Sir.
So flow of current in the semiconductors. So the flow.
Sir, your voice is breaking.
Now, are you able to hear me?
Yes, sir.
What about now? Audible? Audible?
Yes, sir.
Yes, sir.
Okay. So the field of electronics if you so the electronics era came into existence with the invention of vacuum tubes in the year 1897, and so the first invention was vacuum diode and vacuum triode. And what is the drawback of this device? They are bulky and consumes more power. So these problems are overcome by after the invention of transistors. So the William Shockley invented this transistor device in the year 1948, and there are two materials used in transistor device. One is silicon and germanium. So silicon is most widely used as a semiconductor material for the transistor making, and so developments next rapid development starts after the invention of integrated circuits. Integrated circuits, the most complicated. So integrated circuits. So we can fabricate thousands of transistors on a single chip. So we can reduce the size of the electronic systems further by using this integrated circuits. And I already given the definition of electronics, and these are some of the applications of electronics. So electronics applications are wide. You in home appliances, audio video systems, consumer devices, storage devices. So last class I discussed about this applications of electronics, and we classified the materials into three types: conductors, semiconductors, and insulators. Semiconductor is a material whose conductivity is between conductors and insulators. So conductor has more number of free electrons than semiconductors. So the conductivity of the conductor is more. And so the number of free electrons in the valence band decides the flow of current, the rate of flow of current. And because these electrons are loosely coupled to the atom, so and also we define the electric charge. So what is the electric charge? Is the electrical property of the matter. So because of an excess or deficiency of electrons, if there are excess number of electrons, then excess number of electrons, the material is negatively charged. If deficiency of electrons means positively charged, and there exists a force acting on the charges. So this force, the force act between the charges is evidenced by attractive force or repulsive force. This force is known as electric field. So this is a line of force. It is a repulsive force or attractive force. So Coulomb is number of electrons by charge is measured in coulombs, and it is defined by number of electrons per. So this is and we also define the voltage. So voltage is the potential difference. So to overcome this force, we need some energy to move the charge. So this potential difference or potential energy between the potential energy of the charge is the potential difference or voltage. So it is given by W by Q. And we also define the current rate of flow of electrons in the conductor. So this is the conductor. You can see the random motion of electrons in the conductor. So when the conductor is if the one end of the conductor is applied with a positive charge and another end is negatively, when you apply a potential difference across the conductor, one end becomes negatively charged, other end becomes positively charged, and this repulsive force produced by the negative voltage at the left causes the free electrons to move towards the right. So you can see the direction of electrons. So the direction of electrons is towards right, because these electrons are attracted by the positive voltage at the other end of the conductor. So the rate of flow of electrons is the current. So last class we also defined the resistance. Resistance is the opposition to current. So if the material, if free electrons move through the material and occasionally collide with the atoms. So this collision causes loss of energy, and restrict their movement is restricted. So this opposition to the flow of free electron is called resistance. So the unit of resistance is on R, and conductance is 1 by R, that is Siemens. And these are the various types of resistors, and you all know the color coding of resistors. And we also discussed about the potentiometer, and there are two types of variable resistor. One is called potentiometer, and the other one is known as rheostat. And this variable resistance property is used extensively in majority of the applications. I gave the applications such as thermistors that changes resistance as a function of temperature, photoconductive cells that changes resistance as a function of light, strain gauge that changes resistance as a function of force. So there are three types of sensors. So this operate on the concept of variable resistance. So I showed you the various types of measuring instruments. So what is the use of oscilloscope? What is the use of oscilloscope? Yes, anyone please? What is the use of oscilloscope? Anyone please? Am I audible? Am I audible?
Yes, sir.
Yes, sir.
So what is the use of oscilloscope?
To
Last class,
find voltage signals.
display the waveforms. So
Waveform.
display the waveforms. You can see the waveforms on the oscilloscope. The sinusoidal waveforms. You can measure the frequency. You can measure the voltage. So everything is all these measurements are possible using this cathode ray oscilloscope. So now the cathode ray oscilloscope has gone. It has very limited usage. So most of the displays are made up of LED materials or LCD materials. These oscilloscopes are known as digital oscilloscopes, not cathode ray oscilloscopes, CRO. So the short form of oscilloscope is CRO, and nowadays we are using digital oscilloscope rather than the analog oscilloscope. And I showed you the breadboard diagram. And last class I I showed this circuits, series circuits resistance. You know how to find the resistance, voltages across the resistance. Last class we did this examples, and I showed this applications of resistors, variable resistors in the water level indicator. Okay, that's all about resistors. So what is the property of capacitor? Resistor is opposition to the current. What is the property of capacitor? Can anyone? Yes, what is the property of capacitor?
So it stored charges.
Store charges. How it store charges? How it stores?
Yeah, I
Huh?
guess just with the help of electric field.
Yes, with help of electric field. So if so, what is actually a capacitor? Capacitor has two parallel plates separated by a insulator. So this is the construction of capacitor. You can see the two plates, parallel plates, conducting plates, separated by insulating material called dielectric. So when you apply a DC source, when you connect the DC source across this capacitor, so this you can see the one lead is positively charged, other lead is negatively charged, and you know that there exists a electric field between these opposite charges, and so this capacitor stores energy in this electric field. So a capacitor stores energy in the electric field established by opposite charges on the two plates. So the electric field is represented by line of force. Already I have shown the electric field. So W is equal to 1 by CV square. So when you connect the battery, electric field between the plates which stores the energy. So C is equal to Q by V, Q is equal to CV. C is the capacitance, Q is the charge. And so what are the different, there are different types of capacitor, plastic film capacitor, ceramic capacitor, electrolyte capacitors. And we have also variable capacitor similar to variable resistance, potentiometer. The name of the variable capacitor is known as trimmers. So trimmers, by adjusting this screw, we can adjust the separation between the plates, so we can vary the capacitance. And there is one more material called varactor diode. So varactor diode is a semiconductor material, so which exhibits capacitance characteristics that is varied by changing the voltage across the terminals. By changing the voltage across the terminals, we can vary the capacitance. And I've showed this capacitor circuits, series capacitor circuits, and you know how to find the voltage and current across the capacitor and resistor, right? Any doubt in this up to this point? Any questions?
No doubt, sir.
Okay. So let us. This is a charging action of a capacitor, and when you connect the battery source across the capacitor, the one end of the plate is positively charged, other end is negatively charged. When capacitor is fully charged, it does not allow any current through it. So the fully charged capacitor blocks DC. Fully charged capacitor blocks DC component. So capacitor blocks DC component. And this when the fully charged capacitor discharges through some conductive conductor. So if, a very low resistance, the conductor is connected across the capacitor with a switch. When the switch is closed, capacitor is charged up to 50 volt, and switch is closed. The excess number of electrons on the plate move towards the circuit to plate A. Resistor current flow through the low resistance and low resistance of the conductor. So energy stored by the capacitor is dissipated in the resistance of the conductor. So energy stored in the capacitor is dissipated by the resistance of the conductor. So this is how the capacitor discharges energy. And the important parameter of the RC circuit is RC time constant. So the RC time constant is fixed time interval that equals the product of resistance capacitance in a series RC circuit. So the time constant is expressed in seconds and resistance is in ohms and capacitance in farad. So tau is equal to RC. And what are the applications of capacitor? Do you see any application? Capacitor stores energy. Where is the need of storage of energy? Studied reactance, capacitive reactance, inductive reactance. Yes or no? What is the expression of capacitive reactance? Xc. Xc is equal to what?
So 1 divided by omega c.
1 divided by omega c. So this reactive elements also opposes the flow of current, right? This reactive elements, similar to your resistance, this reactive elements also opposes the flow of current. And this opposition is very useful in rectifier circuits. What is rectifier? Rectifier converts. So I'll show you the rectifier. So don't. So you can consider the rectifier as a black box. So the input signal is a sinusoidal waveform. The input is a sinusoidal waveform. Output is somewhat pulsating DC. Not exact DC. It's a pulsating DC. So rectifiers converts this analog, that is AC, AC into DC. So you can see that output of the rectifier. So the rectifiers, the basic element of the rectifier is a diode. So diode allows current only in one direction, and it blocks the flow of current in another direction. So we'll get only positive cycles at the output. For full wave rectifiers, there will be two diodes. So one diode will allow direction positive cycles, the other diode will allow negative cycles. So you will get both cycles. But output is not a pure DC. DC means straight current, direct, that is constant voltage. But you can see the voltage is not constant. So how to obtain this pure DC? So you can use some filters. So here we used capacitor as a filter. So what is the use of this capacitor in this rectifier? So capacitor, you can see the charging and discharging action of the capacitor. Capacitor charges through the resistor and quickly charges through the resistance of the rectifier. So the capacitor will follow the rectified output curve up to the peak value. So up to the peak value, it follows the rectified output voltage. As the rectified voltage passes the peak, so as the rectified voltage passes the peak, the capacitor begins to decrease, that is begins to discharge very slowly through the resistance. So this is the discharging action of capacitor. This is charging action of the capacitor. So this is the output waveform of the capacitor. So you can see this, the quality of output is somewhat improved by the capacitor. So capacitor is used for filtering applications, especially to remove the ripples in the output of the rectifier. And it is also used as a blocking element. DC, already I told these capacitors block the DC signal. So when you want to design an amplifier, normally the amplifier circuit consists of more than one stages. So you can see the block diagram of the amplifier. There are two amplifiers connected in series. So why we use two amplifiers? To increase the gain. So what will happen if any DC signal in the amplifier 2, this will be this DC energy will flow towards the amplifier 1. So we need to block this DC signal. So we use capacitor for DC blocking. And capacitor is also used for bypassing the AC voltage, alternating voltage around the resistor without affecting the DC voltage across the resistor. So in amplifier circuits, for example, DC voltage is called bias voltage required at various points for amplifier to operate properly. So a sufficient large capacitor connected from the bias point to ground provides a low reactance path to the ground for AC voltages. So capacitor bypasses the AC voltages, leaving a constant DC bias voltage at the given point. So these are some of the applications of capacitor, and the capacitors are used in signal filtering. So signal filtering is required in all the receivers, whether it's a television receivers or a radio receivers. You need to tune your receiver to the particular station. How will you tune the receiver to the particular station? You need to adjust some capacitance. So by varying the capacitance, you can adjust the resonant frequency of the filter, and you can select the particular station. So all the TV receiver has some form of filters to select the particular station. These filters are constructed using this capacitors. So this, the next passive element is inductance. So inductance stores the inductance. When the length of wire is formed into the coil, it becomes an inductor. So current through the coil produces an electromagnetic field. So current through the coil produces electromagnetic field. So inductance stores energy in the magnetic field. And the relations of the inductor, W is equal to 1 by Li square. So I is the current. So what is the L? L is the inductance. W is the energy. And similar to the RL time constant, we have RL time constant, which is equal to L by R. And inductances are used to remove the noise in the, suppose if the two circuits are connected in series, and because some noise will emerge from circuit 1 to circuit 2. So we need to prevent this noise. So we can use the inductive filter to remove the noise. So these are the applications of inductor, the rail systems. So it used to prevent the radiated noise, and we use RF chokes, the radio receivers, for blocking very high frequencies called radio frequency RF chokes. So electromagnetic interference. So interference because so more number of signal present at the receiver, we need to block the unwanted electromagnetic signals, and we can use the inductance to block the electromagnetic interference. So the unwanted signals are known as interference. So the RF chokes are used in that purpose. And by using this RC circuits, that is the inductance and capacitance circuit. If the inductance and capacitance are connected in parallel, it acts as a tank circuit. Tank means stores energy. So this is used as a tuned circuits. Tuned circuit means select tuned to the specific frequency. Because all the radio stations are operated at separate frequency band. So we need to select a particular station from the different stations. So this is achieved using some tuned circuits. So tuned circuit are normally consist of capacitor and inductor connected in parallel. So that's all about the. So I introduce the material used for the electronics, that is semiconductor material, and is some basic aspects of semiconductor material. And here I introduce the passive elements and application of passive elements in the real world. Uh, so that's all about the fundamentals of the passive elements and some of the important terms associated with the passive elements. That is voltage and current, electric field. So you should be familiar with the these important terms. So what is current, what is voltage, what is charge, and what is electric field. So whether it's electronics or electrical engineering, we always use these terms: voltage, current, electric field. So any questions? Any questions up to this point? Any questions?
No, sir.
No, sir.
No, sir.
Okay. So if you have any doubts, you can ask me freely. Um, so you have to be attentive in the first few classes. Otherwise, it's difficult to cope up with the subject. So not only for this subject, you have to be attentive in all other subjects, especially for the first month, first 4 weeks. Once you understood the fundamental concept or fundamental ideas of the subject, so you can easily understand the further topics of the course. So please be attentive, and if you have any questions or doubt, you can ask me. Um, Next, you open LT Spice screen. All of you open LT Spice screen. LT Spice screen is ready. Yes or no?
Yes, sir.
So first we start with some.
Yes, sir.
So first we start with some simple circuits. I wanted to know whether you are familiar with whether or not you are familiar with the construction of circuit in LT Spice and measurements of the circuit. Okay, first all of you construct this simple resistive circuit, and I need a value of current. I need a value of current. Sorry, this circuit. I2, I3, I4. And you have to verify these values with your theoretical expression. You know how to find the current values, right? I2, I3 by applying Kirchhoff voltage law and current law, you can easily find the currents through the resistors. And you have to verify these values through the measurements. So all of you construct this circuit and tell me the answer. I want the answer for I3, I4.
Sir, can you show the diagram again?
This is the diagram.
Okay, sir.
Finished? Ma'am, you can also simulate this in the LT space, ma'am. Mom Mageshri, ma'am. Hello? Rashida, ma'am.
Yes,
Rashida,
sir.
ma'am. So you can simulate this in the LT space, ma'am, and show to the students. Is it?
Let me try.
Okay, ma'am. Because I don't know about all the students. Some of the students may not be knowing how to. So we can construct the circuit in LT space and can demonstrate this to the students how to take the voltage and current. Doing this, anyone finished? Anyone finished?
Yes, sir.
Sir, 1 minute, sir.
Yes, sir.
Okay, sir. Thank you. Completed, sir.
So, can you share your screen? Can you share your screen so that others can also see your circuit diagram and measurements? Who said completed?
Sir, me, sir, but I'm not sure whether it's right, sir.
Okay. Can you share your screen so that others can see?
Sir, no, sir.
Okay. So anyone else or
Sir, I've also completed.
can you share your screen?
Yes, sir. But I don't think I have the access right now.
I'll give you access. Yes. Can share your screen. Okay, this is a circuit diagram. All of you constructed the circuit and set the voltage values of the source. Yes or no? This step is done.
Yes, sir.
Okay, what is our open the voltage source? Open the voltage source so that others can also see how you fix the values. V1, open V1. So V1 is DC voltage of 5 volt and resistance values are chosen. Now how will you see the current and voltages? How will you see the current and voltages? Suppose I
Yes,
want,
ma'am.
suppose in the graph form,
So we just place the cursor on the
Yes.
registers.
So what is the current value of I2?
Sir, I2 is 9.3 milliamps.
So all of you please cross check your answer. Um,
Yes, sir.
3.45, I2 is 9.29. So are you getting the same values?
Yes, sir.
Yes, sir.
Okay, so you are familiar with the construction of circuit in LT Spice and how to measure the voltage and current. Okay.
Sure, I have completed.
Who is completed?
Sure. Megha Vikavaitya.
Okay, complete. If any questions, you can ask me. Otherwise, no need to share as of now.
Yes, sir.
Sir, what we have to take in the stop time and else?
The stop times are not required. This is simple DC source, right? We are not
Yes.
giving any AC signal. So we are just giving a DC signal. And by placing the probe on the resistor, across the resistor, you can easily read out the values. And you can see
Yes,
the
sir.
graph. Yes?
Yes. Actually, sir, we are using after a long time. That's why.
So, ma'am, Rashida, ma'am, you completed the circuit, ma'am. I don't have the circuit. Uma Mageshwari, ma'am. So, Naman Kumar, please
Yes, sir.
share your circuit and explain to the.
Sir, you made me a attendee. I'm not the presenter.
Yes, I changed the settings. Okay, sorry, Naman Kumar, right?
Yes, sir.
Okay, okay, can share your screen.
Sir, can you say it?
Yes. So he wanted to know how to see circuit connection is clear, right? Any doubt in the circuit connections?
No, sir.
So circuit connection is no doubt, and application of voltage source is no doubt, and you want to see the measurements. So how will you how did you simulate? Raman Kumar, right? So,
Yeah, sir. I just went to run.
Run, okay.
Then in the transient, I set the stop time as 1. Start saving as 0.1. It's just random thing.
Still not. I think. What about if you choose DC? DC. So there are various analysis, right, in the simulation. So
Yeah.
this only a DC. So transient.
So we have done this transient for DC only if we want to check the current in the graph itself.
Okay, okay, okay. So the
So
start time is what is such a value of start time?
start saving data is 0.1.
Okay. Next parameter is.
Sorry, sir.
Next parameter. What are the parameters in the settings?
It's the stop time, which is 1. Time to start saving data is 0.1. And maximum timestamp is 0.2.
These are the standard values or
So these are the values that we were told to set.
start time. Okay, this is actually used in the AC analysis. If you apply a sinusoidal signal to the circuit. Okay, after this, what you did?
Just clicked on OK, and the blank graph will come.
Okay.
To check the current of resistors, we just need to hover over the resistor and click on it.
For voltage,
So for voltage, we need to click on this point, this
probe.
cursor.
Yes, probe. That is called
Yeah.
probe. Yes.
Yeah.
Now we understand.
So
Yes, tell me.
yeah. So for resistance 1, it is showing. We can zoom over here. It's 8.93 milliampere.
Okay.
Similarly, for R2, it is showing 9.3 milliamps.
Okay.
R3, it is showing 5.85 milliamps.
Okay. Okay. So this now will measure the voltage and current in the circuit. Simple resistors. This is DC say, signal and just we measure the voltage and current. So all of you clear with this?
Yes.
Because this is very
Yes,
fundamental.
sir.
Yes.
Okay. One.
Yes, sir.
So you can also verify the this circuit also. You can take down the circuit. You can verify it later also. So these are the values, theoretical values. You can also cross check with your measurements. So this is the second example. You can do it later. If you want, you can do it later. Next, we'll move on to the RLC circuits. Because the semiconductor part is not started in the class, right? Diode. Our first actual experiment is diode characteristics of VI characteristics of diode, volt and ampere characteristics of diode. But started in the class diode. Yes or no? Theory class. Discussed in the class diodes,
No, sir.
construction of diode and VI characteristics are not done in the class, right?
Yes, sir.
So that's better. We will finish the measurements, various type of measurements. So the first example I showed you to familiarize the voltage and current measurements. Next, to familiarize the frequency and bandwidth of the circuit, we'll take this RLC circuits because we will measure the bandwidth of the amplifier. In this course, we are going to design an amplifier, simple amplifier, and we are going to plot the frequency response of the amplifier. So what is frequency response? What is the frequency response? So we have done only voltage and current measurements up to this point, right? In the last semester also, you have done only voltage and current measurements. Have you done any frequency response measurements?
No, sir.
Okay, so this experiment is to make you familiarize about frequency response measurements. So we'll take simple RLC circuits, series RLC circuits, resistor, inductor, and capacitor. So this circuit, when the circuit reactance equal to the, that is, since reactants are equal and effectively cancel, impedance is purely resistive, and the equivalent circuit of this circuit is shown in this second figure. That is, this is the equivalent circuit. When inductive reactance is equal to the capacitive reactance, your circuit can be redrawn like this. So it has only resistance now. Because the capacitive reactance effectively cancels the inductive reactance and the impedance is purely resistive. So what is the resonant frequency? When inductive reactance and capacitive reactance are same, what is my resonant frequency? So resonant is a condition at which the resistance equals the capacitive inductive reactance equals to the capacitive reactance, XL equal to XC. So you know the expression of XL, right? 1 by, what is XL? 2 pi FL. For XC is 1 by 2 pi FC. So equate these two equations and find the
Hello,
resonant.
sir.
Yes.
So omega is equal to 1 by root over LC.
Root over LC. 1 by 2 pi. 1 by
Acha,
2 pi.
yes, 1 by 2. Yes, sir. Yes.
1 by 2 pi root over LC. So you can verify this answer. XL equal to XC is directly I'm substituting the expression of 2 pi FL and 2 pi FC and equating these two, you will get 1 by 2 pi root LC. So this is the resonant frequency of the, this is the resonant frequency of the RLC circuit, series RLC circuit, right? Yes or no? So what is the use of this resonant property? So here the graphs are plotted. That is, this response is known as frequency response. So for various frequencies, the corresponding amplitude is plotted. Corresponding current, corresponding voltage is plotted in this graph. This is the current response. This is resistor voltage response. So you can see from this graph at resonant, the circuit voltage or current reaches its maximum value. Am I correct or not? Am I correct? Because there is no reactance opposition provided by the reactance. Capacitive reactance equals to the inductive reactance. So the reactance element is completely cancelled out, and the impedance is purely resistive. So the voltage across the circuit will be of will be as same as your power supply voltage. Am I correct or not? Yes or no?
Sir, are you sharing your screen?
Okay, I'm not sharing. Sorry. So this is the resonant frequency condition. 2 pi root LC. FR equal to 2 pi root LC. And if you see the graph frequency response of the circuit, so x-axis is the frequency axis, y-axis is the current, and y-axis is the voltage. So this graph is plotted with respect to frequency. That is, voltage and current are plotted with respect to frequency, and you can see the maximum value occurs at resonant frequency. FR is the resonant frequency, which is equal to 1 by 2 pi root LC. Because reactance is cancelled out and the circuit impedance become purely resistive. Understood or not? Understood? Yes or no?
Yes, sir.
So this is called a frequency response of the circuit. Frequency response means x-axis, the current or voltage is a function of frequency. Current and voltage is a function of frequency. It's called frequency response of the circuit. And at resonant frequency, circuit reaches its maximum value. So what is the use of this resonant circuit? What is the use of this resonant circuit? Can anyone tell? I explained the concept of frequency selection in the radio receivers, right? How the particular station is selected based on its frequency, right? Am I correct? How the particular station is selected?
Yes, sir,
Based
based on the frequency.
based on the frequency only. So if you use this type of resonant circuit, you can select your desired frequencies. Suppose your resonant frequency is, suppose I want to select 30 hertz, 30 kilohertz signal. So by changing the values of you can choose the LC values accordingly. Is it possible or not? Is it possible? Yes or no? Because the circuit provides maximum response at the resonant frequency. If you move away from the resonant frequency, the response decreases. And response reaches 0, both the above or below resonant frequency, for both above and below resonant frequency. But this curve is not sharp, but we can for frequency selective filters by improving the value of Q. Q is the quality factor. So do you know what is quality factor? So what is quality factor? Yes or no? Tell me. Are you attending the class or not?
Sir, like peak energy, like maximum energy, something like that, I guess,
Yes.
stored in.
Quality factor is the, anyway, I'll give you the expression. So now we are going to construct the band pass filter. So what is band pass? This is band pass filter because we can consider this as a band pass filter. So what is a band pass filter? It allows some band of frequencies and it blocks the all other frequencies. Am I correct? So you can consider this as a band pass filter characteristics. It allows some band of range of frequencies to pass through it and it blocks the other frequencies. Not completely blocked, but amplitude responses decreases for other frequencies. So a band pass filter allows signals at resonant frequency and at frequencies within that certain band, extending below and below above the resonant value to pass from the input to output without significant reduction in the amplitude. So this is the example of simple band pass filter. The band pass filter can be constructed using a simple RLC element connected in series. Agreed? Agreed or not?
Yes.
So this, so now next is the definition of bandwidth. So definition of bandwidth is bandwidth of a band pass filter is the range of frequency for which the current or voltage equal to or greater than 70.7%, which corresponds to 0.07% of its value at resonant frequency. So this is the value at resonant frequency. At resonant frequency, the gain is 1. So the voltage or current is same as your input voltage, and you can express this in the form of gain also, output by input. So at resonant frequency, gain is 1. That is same output voltage equals the input voltage. So the gain can be 1. Gain is 1. And what is the bandwidth range of frequencies for which current or voltage equal to the or greater than 70.7%? So it corresponds to 0.707. So this point is known as lower frequency, lower cutoff frequency. This point is known as upper cutoff frequency. And F2 minus F1 is the bandwidth of this band pass filter. And this definition applies to all type of circuits, not only for band pass filter and for the other circuits also. And this another common term for upper and lower cutoff frequencies, 3 dB frequencies. So decibel is the 10 times the logarithmic ratio of 2 powers, which can be used to express the input-output relationship of the filter. So we express this gain in terms of decibels. That is 10 log P out by P in. Similarly, this is decimal formula for voltage ratio. It is 20 log because power is equal to I square R. Voltage equal to so this is the voltage ratios 20 log V out by V in. So next,
Excuse me, sir.
yes, tell me.
Can you explain that part again? Decibel measurement. Yes, sir.
Decibel is another the term. Uh, Decibel is a 10 times the logarithmic ratio of 2 powers. So another common term for upper and lower cutoff frequencies, 3 dB frequencies. So what is 3 dB frequencies? What is dB? First we need to define what is dB. dB is 10 times the logarithmic ratio of 2 powers, so which can be used to express the input-output relationship of a filter. P out is the output power, P in is the input power. So the following equation expresses the power ratios in decibels. Similarly, the decibel formula for using a voltage ratio is based on the previous formula for power with voltage measurement across equal resistance. So 20 log divided by V out by V in. This is the other way of expressing the ratios, input and output ratios, whether it's a voltage power ratio or voltage ratio. If we use power ratios, it's 10 log P out by P in. If you use voltage ratios, it's 20 log P out by V in. No need to confuse. Anyway, you will study this in detail. I'm just giving the definition only here. I'm not going into the details of this, and this will be discussed in the class, theory class. So just you have to know the formula for finding the decibel values. Next is 3 dB frequencies. So 3 dB frequency is the output of the filter is said to be 3 dB at cutoff frequencies. As you know, this frequency is a point at which the voltage reaches 70.7% of its maximum voltage at the resonance. So 70.7% corresponds to 0.707 of the maximum voltage at the resonance. So you can output voltage divided by maximum value. So the Vmax will be get cancelled, and you will get minus 3 dB. So we measure the bandwidth in terms at 3 dB point. So we measure the bandwidth of the circuit at 3 dB point. As I told, the frequency selectivity of the circuit, is determined by the quality factor of the resonance circuit. So the quality factor is reactive power divided by true power. So I square terms cancelled, leaving Q is equal to XL by R. This is quality factor. The circuit has good quality factor, then you will get the sharp response. I'll show you the sharp response. So you can see the graph, 3 types of frequency response. So which one is more sharp? Which color is more sharp?
Blue color.
Yes.
Blue, sir.
Yes. This. So in order to get the sharp response of the filter, you need to have good Q value. Q value is defined as reactive power divided by true power. So the Q of the resonance circuit is ratio of reactive power to the true power. So I explained about resonance condition, and I also defined what is bandwidth and how to compute the bandwidth of the resonance circuit. And this resonance circuit are very useful in the TV receivers. So the choice of desired station is depends on the resonance circuit. And so the resonance circuit is given, and its value is also given. So what you have to do is you have to construct this resonance circuit in LT spice, and you have to measure the bandwidth. So what is the bandwidth of this circuit? What is the Q factor? And what is the resonant frequency of this circuit? Can anyone tell? I give the expression of resonant frequency, right? FR equal to 1 by 2 pi root LC. So L is given, C is given. And the effective resistance, that is L has internal resistance of 50. So you can add this resistance along with the 51 ohm. So the total effective resistance is 50 plus 51. So 101. So find out the value of FR and the Q. Doing? Doing or not? Doing or not? Anyone found? Yes, calculated or not? Yes, done. 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 Anyone completed?
No, sir.
Simple calculation. Yes, fine. Found. Naman Kumar found. Naman Kumar.
Yes, sir. Just a minute.
This is the answer. So please note down this answer. FR equal to 1 by 2 pi root LC, which is to other 3.2 kilohertz. XL is equal to 2 pi 1.46 kilo ohm, and Q is 14.5, and bandwidth is FR by Q 1.6 kilohertz. Right? Note down this. Found. Are you getting the same answer? Are you getting same answer or not?
Yes, sir.
Okay, now what you have to do is you have to construct the circuit in LT spice and you have to verify the same answer, bandwidth. So you are going to plot the frequency response of this resonance circuit and you have to verify practically that the same bandwidth is coming or not. I'll tell you how to take the frequency response measurements. First, you construct the circuit in LT spice. Is that fine? Is that fine?
Yes, sir.
Yes, sir.
Okay, construct the circuit first. So you require capacitance and inductors. Inductor and resistor, right? You can connect all this. So what you will have to apply voltage, right? My screen is visible.
Yes, sir.
Yes, sir.
Okay. So connect the voltage source as usual, and so I constructed the circuit. So next, what is the value of capacitance? What is the value of capacitance? Point not 47 microfarad. So microfarad you have to give U, right? So this is point not or point. Point not 7 microfarad. Okay. Point not. Value is correct. So what is the value of inductance? 10 millihenry, right? 10 millihenry. So set 10 millihenry in this 10 millihenry, and internal resistance is given as 10 ohm. So series resistance is 10 ohm, 10 millihenry. What is the resistance? 51 ohm, right? So the resistance value is 51 ohm. 51 ohm. And connect the ground. Or have you done this up to this?
Sir, I think you have put comma instead of
Huh?
point in the
Capacitance.
capacitance.
How to change these values? You have to right click.
Right click on it on the C.
Right point. Now it's correct, right? Now it's correct.
Yes,
Yes,
sir.
sir.
Yes, sir.
So all of you have constructed this circuit. Next, we have to set the input waveform. We have to give it as sine wave. So go to the advanced setting, sine wave. You can choose the amplitude as 10 and frequency as you can give any 100 or something. And in the AC amplitude, give 1 volt. You finish these settings as per the then. So in the voltage source, you have to select sine wave, and amplitude you have to give any value like 10, and frequency can be 100. Once it's done, give OK. Now I have given the input signal to the filter. What is the next step? Need to see the next step is to simulate, right? So for simulation, go to AC analysis and type sweep. You give decade, and number of points can be 100, and start frequency can be 10, and end frequency can be 10 gigahertz. Have you set these values in AC analysis?
Yes, sir.
Now give OK. Now if you connect the probe, so this is what your frequency response and phase response. Now I have plotted the frequency response and the phase response of the RLC circuit. This is a band pass filter. So band pass means it allows only certain range of frequencies. Now we have derived the expression of the, we obtained the value of the resonant frequency of the circuit. It is, what is the value? Resonant frequency of the circuit? 1.6 kilohertz, right? Yes or no?
Yes, sir.
Yes, sir.
So how will you measure the same values in the graph? So what point you have to select? So you have to choose minus 3 dB, right? Maximum gain.
Yes,
From
sir.
maximum gain is, what is the maximum gain? You can see the read out the values straight away in the. So suppose I chosen this point. So what is my dB? It is minus 2.80 dB, right? So you can see the x-axis values and y-axis values at that point. 22.965 and minus 2804 dB, right? Am I correct or not? Are you getting the same answer? Maximum y-axis is minus 2.80. Yes or no? Are you able to see the values? Yes or no?
Yes, sir.
Yes, sir.
So the highest value of this highest response is minus is coming as minus 2.8, right? So minus 3 dB means what is the value? What value you have to choose? 2.8 minus 3 dB is how much? Is approximate 2.3 minus 3. So it is 5.3 minus 5.3 dB, right? So you can place the cursor at minus 5.3 dB. Are you able to fix the values?
Yes, sir.
So calculate the bandwidth now, F1 minus F2. So this is F1, that is 23.7 kilohertz. What is the answer? 5.3. 5.3. How to choose the correct value? So what is the corresponding frequency at 5.3? Anyone, please? How to place the cursor, ma'am? Nashida, ma'am? Processing add trace. How to add the trace? Right click manually to enter the horizontal axis. Right click. Um, Right click to manually enter not to access. So even able to choose the correct value of dB. Yes or no? Anyone have done this? Or is there online?
So doing it, sir.
Now what is the bandwidth? Are you getting the same as theoretical value? Okay. You can choose this. I think cursor, magnitude. You can choose minus. What is the value? Minus. Ashida ma'am and Uma Maheshwari ma'am, what you are doing, ma'am?
Sir, excuse me, sir.
Yes, I told you to.
I just completed this one only.
Okay, ma'am.
I'm just I'm confusion with the values. That's it.
I think you have done this lab earlier also.
No, I'm just trying and started working on now itself. I just attending the lab parallelly, other two labs. Just started.
Do this and tell the students.
Okay. So can you please share the next experiments?
Okay, I'll share the next.
Upcoming experiments. Okay.
For next week, I'll tell you, ma'am.
Okay, sir. Then I can, prepare for academic.
So it's approximately as 5.9, 4.9, 4.9.
Sir, we are checking for the peak point, right?
3 dB point. I think it's somewhere 5 point. I think 22.1 kilohertz. You can roughly take as 22.1 kilohertz is F1 and F2 as F2 25.
Sir, F2 is 24 and F1 is 22, around 22.
Okay, what is the bandwidth? What is the bandwidth? F2 minus F1 is how much? F2 minus F1 is how much?
So 2.
1 point? Somewhere around 1.6 or 2, right?
Yeah, 2.
So
I could calculate it to 2.
Are you able to select that particular point?
Sir, I just zoomed in. So then I could check.
Okay. So I think the x-axis, the first point occurs at 5.6. So 5.6, it's 22.9. 22.9, right? 22.5. And the second point is 24.5. So 24.5. 24.5. 24.5 minus 22.9 is 1.6 coming correct. 1.6, somewhere around 1.6. So this graph is known as frequency response of the circuit. All of you got this graph? All of you got it? Yes or no?
Yes, sir. I have shared an image of that peak point.
Okay, I'll show you. This image are getting like this. Okay, the range you have selected. Okay, so you selected some other range, right? So you can plot.
I just clicked and dragged in that area of peak point.
In the simulation setting, you can decrease to 10 megahertz. 10 megahertz. So you will get some exact graph.
Sir, in this graph only I zoomed in. That's all I did.
Oh, or else you can also limit the range.
Yes.
You can also limit the range. So to get the yes, you can change the settings also here. On screen. So instead of gigahertz, let us use megahertz.
Excuse me, sir.
Yes.
So actually, this is our break time. So actually, we have classes after that also.
Okay, can leave.
Yes, sir.
All of you done this experiment?
Yes, sir.
Okay, next class I'll explain it clearly.
Yes, sir.
So next class we'll
Yes.
continue. Okay, thank you all. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Your attendance.
Attendance, I'll take it from the list. Okay. Rashida ma'am and others call, please remain in the.
Okay, sir.
We'll discuss what to do in the next class.
Okay, sir.
Others can leave the meeting. So how many basic electronics lab for you, ma'am? Only you are taking this slot or going
No,
going
sir.
for
Last week I have started 2 and
okay.
with this, and then total it's to be 4
Oh,
from next week.
the same lab for 2 slots or 3 slots, ma'am?
4 slots actually. From next week onwards, it will be 4.
Okay, madam. What about Uma Maheshwari? What is her name?
I'm also having Uma Maheshwari, sir.
Okay, ma'am. Okay, ma'am.
I'm also having the same lab for 4 slots, sir.
Ma'am, don't mistake me. There are 70 students, ma'am. So I need a help of your research scholars, ma'am.
Yes,
So
sir.
that's why please do some basic experiments in LT Spice, ma'am. And I think you are clear with the basic measurements, right?
Yes, sir.
Measurements at all you are, ma'am?
Yes, sir.
Measurements, frequency response measurements, voltage, current measurements, circuit diagram construction.
Yeah, I know the construction, sir.
Yes, ma'am. Construction, where the measurements. What about measurements, ma'am?
But measurement also, sir, but I'm not familiar with this LT space, sir. That's the problem. So I'll learn it, sir.
Yeah, you can learn it, ma'am. I will share you the material if you want. Please.
Okay, sir. Sure.
So from the next class, I'll give the list of what experiment you have to do. I'll
For the
share.
experiments, okay, sir.
And please do it in your free time, ma'am. And
Okay, sir.
because if some students is asking doubt, means we need to clarify it.
Okay, sir. Okay, sure, sir.
Because I can't do it for there are 70 students in the lab.
Okay, sir.
Please learn some LT Spice, ma'am. That is circuit construction. At least since I need help in your circuit construction and verification of results. And if any error in the readings or response, you have to help them, ma'am.
Okay, sir. Sure, sir.
I'll definitely tell you the next experiment about the next experiment before coming for next class.
Okay, sir. Sir,
Okay.
is it okay to complete the experiment before we are coming to the lab? I mean, by
Lab,
ourselves?
Yes, ma'am. I have the circuit, ma'am. I'll give you the circuit diagram to try to simulate the circuit in your LT Spice. And
Okay. Before
yes,
coming to the lab, then it is
yes.
okay to clarify the doubt. That's why.
Yes,
If
yes.
you are doing with the student, it will be very difficult because we are also
Yes. I'll give you the
So
circuit.
how many? Okay, sir. How many experiments we are going to do in the lab, sir, for every session?
It depends on the ma'am because they have not started the semiconductor devices diodes. So
Okay, sir.
their experiment. You have the syllabus copy, ma'am.
No, sir.
So in this course,
Don't have.
we are mainly going to do the BA characteristics of the device, transistor,
Diode. Okay.
diode,
Transistor diode. Okay.
and the basic configuration of a transistor, CE, CB, CC, and
Okay.
we are mainly doing voltage and current measurements. And for amplifier, we have to do frequency measurements also. That's why I explained the frequency measurements in today's.
Yes.
So once they are thorough with the measurements, and they can easily take up take up the experiment, and they can read out the values.
Yes, sir.
Okay, ma'am. Next from next class onwards, please ask me before they are coming to the lab. I'll give you the circuit diagram, or we can create a WhatsApp group also. So we can.
Sir, it's better to.
That will be better, sir.
Sir,
Yes,
that will
ma'am.
be better,
excuse me,
sir.
sir.
Yes, tell me.
This is Shakeen. I've also been allotted in this lab. I've asked you permission today morning.
Okay, ma'am. You joined now
Yes,
only.
sir. Yes, sir. No, I've joined it by 12:40, sir.
Ma'am, you please three research research scholars, please do some LT spy experiment, and
Yes, sir. Yes, sir.
you have to be thorough with the measurements, especially measurements.
Yes, sir.
How
Yes,
to
sir.
take
Yes, sir.
the frequency response, how to measure voltage and currents, and so any settings also, the settings of your power supply settings, and AC analysis, DC analysis. I'll give the introduction. I'll give introduction about the experiment, and I'll tell you how. I will tell them how to what are the parameters needed in the experiment, and they will do this experiment on their own. But if they ask for any help, in the settings or
Taking the measurement. Okay,
especially they'll ask doubts in the measurements and
Or,
settings.
yes, okay, sir.
Okay, sir. Okay, sir. Yes,
Okay.
sir.
If you done, okay, sir.
So you
Okay, sir.
be clear with the measurements and settings, ma'am.
Yes, sir. Sure,
I,
sir.
I need your help only in the measurements and settings.
Okay, sir.
Okay, okay, sir. Okay, sir.
Okay, thank you, ma'am.
Excuse me,
Thank you.
sir. Please
Yep.
make a
Thank you,
WhatsApp
sir.
group for.
Yes, ma'am.
Please create a WhatsApp group for us.
We'll create an
Only for the
WhatsApp group,
research
sir. In
Ah,
that
okay.
you can share the experiments. Then we'll
Yes,
we'll do before itself.
Okay, ma'am. Okay, ma'am.
Yes.
You can also create WhatsApp group and share the unit link, ma'am.
Link.
Yes, sir. Yes, sir. Okay, sir.
Thank you, ma'am. Thank you, ma'am. Thank you, ma'am.
Thank you.
Thank you,
Thank you.
sir.
Thank
Thank
you.
you,
Thank you,
sir.